Okay, so you know when you spin a basketball on your finger, you can see it rotating,
Right.
right? Well, get ready, because spin in quantum physics is a whole other story. It's not about actual spinning at all.
No, not at all. It's really more of a fundamental property, kind of like it's built in, like mass or charge, an inherent property.
So, like, I shouldn't be thinking of electrons as these tiny planets whizzing around.
Nope, not at all. There's no physical spinning involved. It's got angular momentum, sure, but that doesn't come from actual rotation.
Okay, I think I'm starting to get it, but if an electron isn't spinning, what does it even mean to say it has spin?
Hmm. Well, think of it like this. It's a way to describe the angular momentum that's inherent to the particle. Like we said, we usually associate angular momentum with things spinning, but in this case, there's no actual rotation. And the fascinating part is that this momentum is quantized.
Quantized, meaning,
It can only take on very specific values, like discrete values, not just any random value.
so like steps on a staircase. You can only be on one step at a time.
Yeah, exactly. And those steps are the specific quantized values of spin. It's not a continuous spectrum, but these distinct states.
Okay, so spin is kind of like this rule book for how these tiny particles behave.
Exactly. It's woven into the very fabric of quantum mechanics and influences so much, from how atoms are structured to, like, the behavior of magnetic materials.
Oh yeah, magnetism. I was reading about how electron spin is key to how some materials become magnetic.
It is. Each electron with its spin acts like a tiny magnet, with its own north and south poles, and which way that mini magnet points is determined by the spin state of the electron.
So like in a bar magnet, are all these tiny electron magnets lined up making one big magnetic field?
That's the basic idea. It's not quite as simple as that, though. Like in iron, the spins of the electrons align because of how they interact with each other, and it's this alignment that creates the magnetic field we can see.
So it's like all these electron magnets are doing a synchronized dance, and when they're in sync, boom, magnetism.
Haha, I like that. It's a very elegant way to put it.
But not everything's magnetic, so I guess this alignment doesn't always happen.
Exactly. In a lot of materials, the electron spins are just randomly oriented, so they kind of cancel each other out. So no synchronized dance, no magnetism.
Gotcha. But I also read about this thing called the Pauli Exclusion Principle, which says two electrons can't be in the same quantum state at the same time. So how does that work with spin? It seems like they'd always be running into each other.
Well, that's where spin comes in. You see, electrons can have two possible spin states.
Up and down.
Yeah, you got it. And this helps define their quantum space.
So to avoid a quantum traffic jam, two electrons sharing the same energy level have to have opposite spins, like one up, one down.
Exactly. It's like they need their own designated spots, and their spin creates those spots, which is super important for how atoms are structured and how they form bonds.
Okay, this is all fascinating. But how do scientists actually KNOW particles have spin? Can they see it under some super microscope?
You can't see it directly. We have to get clever with experiments, usually using magnetic fields.
Magnetic fields, huh?
Yeah, one of the most famous experiments is the Stern-Gerlach experiment, where they shot a beam of silver atoms through a magnetic field, and this field wasn't uniform, had a specific shape.
Okay, and
Well, if atoms didn't have spin, you'd expect them to just fly straight through with a little deflection, but that wasn't what happened.
I bet it wasn't. What did they do then?
The beam split in two, and each of those beams was deflected in a different direction. This splitting proved that the atoms had this property interacting with the magnetic field, their spin.
Ah, so they figured out atoms had spin because of how they reacted to the magnetic field.
Clever.
Exactly. And not just any spin. Because it split into two distinct beams that showed that the spin of these atoms was quantized, meaning, again, you can only take on specific discrete values.
Wow, so it proves spin exists, A&D, that it's quantized. That's pretty amazing for one experiment.
Yeah, it was really a big deal. It solidified the whole concept of spin and its quantized nature.
Yep.
It was a pivotal moment for quantum physics. So to sum up, spin is a fundamental property of particles. It's quantized. It's definitely not about actual spinning. And it has a huge GG impact on how things work at really small scales. It plays a key role in magnetism and how atoms are structured, all that. But how do scientists actually measure spin these days? They're not still chucking atoms at magnets, are they?
Haha, no, the methods have definitely evolved. The principles are the same, though. Nowadays, scientists use sophisticated techniques like electron spin resonance, ESR, and nuclear magnetic resonance, NMR, to really dig deep into spin.
Wait, NMR, that sounds familiar. Isn't that connected to those MRI scans you get at the hospital?
You got it. MRI is just a medical application of NMR, which shows you how this abstract idea of spin is being used in everyday technology.
So from a fundamental physics experiment to a medical imaging technology, it's amazing how a discovery about something so tiny can have such a big impact.
It really is. It shows you how interconnected everything is, you know? Understanding the basic building blocks of matter can lead to these incredible advancements in technology and beyond. But the story of spin doesn't end there. We're just getting started, really.
Oh, now you've got me hooked. What else is there to uncover?
Well, one of the craziest things is spin's role in entanglement. That's where things start to get really spooky.
Entanglement. Okay, you can't just drop a bomb like that and not explain. Tell me more.
All right, imagine two particles, let's say electrons, and their spins are linked, like inherently correlated.
So they're like a matched set, but with opposite spins.
Exactly. But here's the weird part. Even if you separate them by a huge distance, their spins stay connected somehow. If you measure the spin of one, let's say it's up, you instantly know the other one is down, no matter how far apart they are.
Wait, so you're telling me that measuring one instantly affects the other one, even if they're miles apart or light years apart? How is that even possible?
That's the thing with entanglement. It just doesn't make sense with our normal ideas about cause and effect. It's like they're communicating faster than the speed of light, which, should be impossible. Entanglement suggests there's this deeper connection in the universe than we thought.
Okay, this is definitely blowing my mind a little bit. So not only is spin crucial to magnetism and the structure of matter, but it's also connected to this bizarre phenomenon of entanglement. Spin really is everywhere.
That's the beauty of quantum physics, right? It reveals this universe that's way stranger and more connected than we could ever imagine. And spin is one of the keys to unlocking its secrets.
It's all incredibly fascinating, but if spin is so fundamental, and we're figuring out how to manipulate it with things like ESR and NMR, could this lead to some wild new technologies?
That's actually a question driving a lot of the research right now.
Hmm.
Being able to control spin at the quantum level could lead to breakthroughs in fields like quantum computing, spintronics, even medicine. But those exciting possibilities will have to wait for another time. The potential of spin is pretty huge, actually. But before we get too far ahead of ourselves, let's go back to that connection between spin and magnetism we were talking about earlier.
Yeah, I'd like to dig into that a little more. Still wrapping my head around how these super tiny electron magnets actually create the kind of magnetism we see and feel every day.
Right, so it really comes down to how all those electron spins within a material behave together. Like in certain materials, let's say iron, for example, the way the electrons interact makes their spins align in the same direction.
So they're all pointing the same way.
Yeah, and that makes their tiny magnetic moments add up, and you get a bigger magnet field that we can actually observe and measure.
So it's not enough just to have electrons with spin. They have to be interacting in a specific way for a material to be magnetic.
Exactly. It's like, think of an orchestra. If all the instruments are playing random notes, it's just noise, right?
Yeah, a cacophony.
Haha, exactly. But when they all play together in harmony, the sounds combine to create this beautiful symphony. It's the same with electron spins. When they all align, their individual magnetic moments add up to create a measurable magnetic field.
Okay, so it's like a symphony of spins. If they're in sync, we get magnetism. If not, it's just noise.
A great way to put it. And that's why not every material is magnetic. In some materials, the electron spins are just all over the place, randomly oriented, so they cancel each other out. No synchronized spin symphony, no magnetism.
I think I'm getting it now. So the material structure, how the electrons are arranged and how they interact, that all determines whether we get magnetism or not.
You got it. It's all about the collective behavior of those spins.
Cool, cool. But you mentioned earlier those advanced techniques, ESR and NMR. They both use the way spin interacts with magnetic fields, right?
They do, yes.
Can you maybe break it down a bit? How do they actually work?
Sure. Let's take electron spin resonance, or ESR, as an example. So what we do is we apply a really strong magnetic field to a sample that has unpaired electrons.
Unpaired electrons.
These are electrons that aren't paired up with another electron that has an opposite spin. So their magnetic moments, they're more free to be influenced by an external magnetic field.
Okay, so they're kind of like lone wolves ready to respond to a magnetic field.
Yeah, something like that. And when you expose these unpaired electrons to the magnetic field, their magnetic moments, they want to align with it. But remember, spin is quantized, so the electrons can't just smoothly adjust their alignment. They have to flip between those discrete energy levels up and down.
Right, the staircase analogy.
Exactly. So they need a certain amount of energy to make that flip, like a quantum push.
Okay, so how do they get that push?
Well, in ESR, we use microwaves. When you hit them with microwaves at just the right frequency, those electrons flip their spins between the energy levels.
So by watching how these unpaired electrons react to the magnetic field in the microwaves, scientists can learn about the material structure and properties.
Exactly. We're essentially using the spin as a tiny probe to investigate the material at the atomic level.
Wow, that's pretty cool. And what about NMR? How is that different from ESR?
So NMR, or nuclear magnetic resonance, is based on the same principle, but instead of looking at unpaired electrons, it focuses on the spin of the atomic nuclei.
You mean like the protons and neutrons in the center of an atom? Those have spin too.
A lot of them do, and that means they have their own magnetic moments. And just like with electrons, we can use magnetic fields and radio waves this time to manipulate and measure these nuclear spins.
Ah, so instead of microwaves, it's radio waves for NMR.
Yeah, and this has had huge implications for lots of different fields, especially in medicine. Remember we talked about MRI being based on NMR?
Oh, yeah, that's right. It's crazy to think this abstract concept of spin that came from physics experiments is now such an important tool for medical imaging.
It really shows you the power of basic research. You never know what practical applications might come out of exploring the fundamental nature of the universe.
Absolutely. Okay, so I think I'm starting to understand the implications of spin.
Yeah.
But you mentioned earlier that spin is also key to understanding this mind-boggling thing called entanglement. Can you tell me more about that?
Okay, so entanglement is where things get really weird, even for quantum physics. Imagine you have two particles, let's say two electrons, that are created in a way that their spins are linked, like they're correlated.
Like a pair, but with opposite spins.
Exactly. But here's the really wild part. Even if you separate these particles by a really big distance, their spins stay connected. It's like they're still linked. So if you measure the spin of one particle, let's say you find it's up, you immediately know the other one has to be down. Doesn't matter how far apart they are.
Wait, so you're saying if I measure one particle here, the other one somewhere else instantly changes its spin? How is that possible?
That's the big question with entanglement. It seems to defy everything we know about cause and effect, about how things work in the world. It's as if they're communicating faster than the speed of light, which, according to Einstein, should be impossible.
So entanglement basically throws everything we thought we knew about the universe out the window.
In a way, yeah. It suggests this deep interconnectedness that we're only beginning to understand, and it all hinges on this seemingly simple property of spin.
So spin is not only fundamental to how matter is structured and the basis for revolutionary technologies like MRI, but it's also intertwined with this crazy phenomenon of entanglement. It's starting to feel like spin is the key to everything.
It really is a fundamental concept in quantum mechanics, and the more we learn about it, the more we realize its potential, not just for understanding the universe, but for developing new technologies that could change the world as we know it. But, that's a conversation for another time.
So spin is involved in all these crazy things. And you said earlier that we've only just begun to understand its potential. What else is out there? What could spin help us do in the future?
Oh, there are so many possibilities. Like, spin-based technologies are already making waves in fields like quantum computing and spintronics. They have the potential to revolutionize how we process information and build electronic devices.
Quantum computing, that sounds pretty futuristic.
Yeah.
How does spin fit into all of that?
It's a bit complicated, but the basic idea is that quantum computing uses quantum mechanics, and that includes spin, to do calculations in a totally different way than regular computers. Imagine a computer that could explore tons of possibilities at the same time.
Like exponentially more powerful.
Exactly. And spin is key to building and controlling these quantum bits, or qubits. You can use the spin state of an electron, or a nucleus even, to represent the 0 or 1 of a qubit. And because of superposition, the qubit can be both 0 and 1 at the same time, so quantum computers can solve problems that would take a normal computer forever.
It's like something out of Star Trek. So what about spintronics? What kind of technologies are they developing there?
So spintronics is about using the spin of electrons, not just their charge, to carry information and do computations. It's like a new generation of electronics that uses both the charge and the spin.
So instead of just moving electrons around to make electricity, we could use their spin to store and process information.
Yeah, think about it. We could have devices that are way smaller, faster, and use less energy. Spintronic devices could be a game changer for data storage. Imagine hard drives and memory chips with ridiculously huge capacity, or transistors and logic gates that work based on spin instead of charge.
Wow, spintronics sounds like it could really change the tech world. Are there other areas where spin could be a big deal?
Oh, absolutely. The potential applications are huge. Like in medicine, we already use spin in MRI to get those detailed pictures of the body.
Yeah.
But imagine if we could actually target and control individual spins inside cells. We could use super precise magnetic fields or other methods to deliver drugs or therapies with incredible accuracy.
It would be like doing surgery at the quantum level. It's amazing to think that studying this tiny property of spin could have such a big impact on healthcare.
Exactly. It all comes back to understanding the universe at its most fundamental level. When we explore the quantum world, we not only discover the secrets of matter and energy, but we also find new possibilities for technologies that could change everything.
This has been an incredible journey into the world of spin. It's amazing to think that something so small can have such a profound impact on the universe and on our lives.
Absolutely. And the best part is, we're only just getting started. There's still so much more to learn and discover about spin and its potential.
Yeah, it's really inspiring to think about all the amazing things that might be possible in the future thanks to spin.
It really is. The universe is full of wonders, and spin is just one example of how something seemingly simple can unlock incredible secrets and possibilities. Who knows what we'll discover next?
Well, it's been fascinating talking to you about spin. Thanks for joining me today.
My pleasure. It's always exciting to talk about the wonders of quantum physics.
And to our listeners, thanks for tuning in. Until next time, keep those brains spinning.